Hello everyone, my name is ANUDEEP and I am going to discuss about frequency domain filtering. First, let's see the characteristics of the frequency domain. Here, this is the DFT equation which is used to convert an image from spatial domain to frequency domain, where x and y are the coordinates in spatial domain, u, v are coordinates in frequency domain. And from the DFT equation, we can observe that the frequency domain function will depend on the spatial domain function for every term, and my term in the frequency domain will depend on all the values of the spatial domain multiplied with the exponential terms. So for except trivial cases, it is usually impossible to find a direct relation between the values of spatial domain and the frequency domain. Frequency is rate of change of intensities in spatial domain. We can relate frequencies in Fourier transform with patterns of intensity variation in an image. Hence, where the intensity is varying very high, we can say that we have a high frequency component there. And when we see a slow varying intensity components like a ball, we can tell that we are having a low frequency component at that place. So edges will be represented as high frequencies and slow varying components will be represented as low frequencies in Fourier transform of the image. Now let's see the Fourier transform of an image using MATLAB. This is the image which we are going to perform Fourier transform. Now we will plot the frequency spectrum of the image, and we will be using inbuilt function FFT2 to get the Fourier transform of the image, and we will use FFT shift function to shift the center of the spectrum from top left corner to center of the image. But as the intensity levels in the image are low, we use gamma transformation or log transformation to the spectrum to brighten the lower intensity levels so that we can see the frequency components clearly. Now let's see the MATLAB code for Fourier transform of the image using gamma transformation. This is the graph of the gamma transformation. Here we can see for gamma less than 1, the graph is like this, for which for lower input gray level values are mapped to the higher output gray level values, so that we can see the lower intensity values in the input image with higher intensity. This is the MATLAB code to find the frequency domain of an image. First we will read the image by the imread function and store it in a variable a1. Now we will show the image with imshow function, and we will apply FFT2, that is Fourier transform, to the image a1, and we will store it in AF. And now we will shift the center of the transform to the middle of the image by applying the function FFT shift and storing it in AF1 variable. Now we will show the image by applying it with great gamma transformation with variable gamma values. This is the input image for which we are going to apply Fourier transform, and this is the output for gamma equal to 0.005. Here we can see the frequency components clearly, and this is for gamma equal to 0.05, and this is for gamma equal to 0.1, and this is for gamma equal to 0.3, and this is without gamma transformation. Here we can observe that without gamma transformation we cannot see the frequency components. We can just see a small dot. By applying the gamma transformation, we can clearly see the frequency components. Now let's see the MATLAB code for Fourier transform of the image using log transformation. This is the graph for log transformation, And here also, similarly as gamma transformation, the lower input pixel values are mapped with the higher intensity pixel values of output. And this is the transformation function of the log transformation. And this is the code for log transformation. Here similarly we stored the image in a variable, and we have applied the FFT2 function for it, and we have shifted the transform with FFT shift, and while displaying it we have applied gamma transformation to it. This is the input image for which we are applying the Fourier transform, and this is the transform of the input image. The input image which we have seen earlier is a scanning electron microscope image of an integrated circuit magnified approximately 2500 times. And in this image we can observe these two white oxide protrusions, which are actually the high frequency components of the image. These high frequency components are approximately plus or minus 45 degrees with the axis. Now let's see the steps in the frequency domain filtering. First, in frequency domain filtering, to avoid wraparound error, we will be padding the image with zeros and create the filter with same dimensions. Generally, we select P equal to 2m and Q equal to 2n, where P and Q are the size of the input image after padding, and M and N are the dimensions of the image before padding. Here, to filter the input image, we will apply the DFT to the input image and multiply the frequency response of the filter to the image, and we will apply IDFT to the response, and we will be getting the filtered image. All the functions are of arrays of size P into Q as the same as the input image. Specification of filter function is simplified by using the functions that are symmetric about their center. So f of u of v should also be centered. To shift the frequency spectrum of the image, that is f of u of v, to f of u minus p by 2 v minus q by 2, that is to center of the image p by 2 q by 2, we multiply the image with e power minus j 2 pi ax by m plus by m, where a equal to p by 2 and b equal to q by 2. On simplification, we get minus 1 power x plus 5. So to center the transform, we multiply minus 1 to the x plus 5 to the spatial domain and apply Fourier transform of it. So now we will compute the DFT of the input image, which will be f of u of v. Now we should multiply the desired filtered function with f of u of v to filter the image. Now we will generate a real symmetric filter function h of u of v of size p into q with center at p by 2 q by 2 and multiply it with the transform of the image to get g of u of v. To obtain the processed image, we apply IDFT for the product f of u of v and h of u of v and shift the center of the transform back. So we multiply minus 1 into x plus 5. Here only real part is considered in order to ignore parasitic complex components resulting for computational inaccuracies. Now let the filter function be h of u of v, that is 0 at the center of this transform and 1 elsewhere. It means we will reject only the DC term of the image and pass all other frequencies of the input image. But we know that the DC term is responsible for the average intensity of the image. So setting it 0 will reduce the intensity of the image to 0. So the resulting image will be like this. It is darker than the input image as the average intensity of the input image is 0. Now let's see the summary of the steps of the filtering in frequency domain. We are given with an input image f of x of y of size m into n, and we have padded it with the parameters p and q, which are p is equal to 2m and q equal to 2n. We have formed the padded image by appending the necessary number of zeros to make the image dimensions p into q. Now we have multiplied f of x of y with minus 1 into x plus 5 to center its transform. Now we have computed the DFT of the image, and we have generated the desired filter function with the center at p by 2 comma q by 2 and multiplied it with the frequency spectrum of the image, and we have found the IDFT of the resulting multiplication. And to again center its transform, we have multiplied it with minus 1 into x plus 5, and we should take the top left quadrant of the obtained image as we have padded zeros to the right and bottom of the image. These are the references used. Thank you.